In Part 2 of Lecture 5, we will discuss first come, first served, and shortest job first scheduling. We will take a look at all of these scheduling algorithms, starting with first come, first served, and shortest job first. Then we will move on to round-robin scheduling and priority scheduling. After that, we will talk about guaranteed and lottery scheduling. We will discuss multi-queue algorithms. And lastly, real-time scheduling. The most basic algorithm for scheduling is first come, first served. Whoever walks through the door first gets taken care of first. What would seem to work well for the local bakery would seem to work well for CPU scheduling as well. But that is not always the case. Imagine that you are at the checkout line in the supermarket, and there is only one person in front of you, a little old lady. The only problem is she is pulling two overflowing shopping carts with groceries for the local hook and ladder company. As you spend the next 20 minutes online behind her, the fairness of the first come, first served algorithm doesn't seem as important anymore. This is also a potential problem in using the first come, first served algorithm as a basis for CPU scheduling, a process that takes excessively long to run, adds to the waiting time of the fastest running processes, and this increases their turnaround and or response times and lowers the system's throughput. We are going to look at the following scenario: 3 processes that enter the short-term scheduling system. The first is the longest by a significant margin. We will assume, for simplicity's sake, that all 3 arrive in the scheduling system within a few microseconds of each other. Assume that P1 did arrive first. Its total processing time is 24 milliseconds because there was no waiting time involved. P2 has to wait the 24 milliseconds for P1 to finish, as well as the 3 milliseconds of execution time that it needs, making its processing time 27 milliseconds. P3 has to wait 27 milliseconds in total, 24 for P1 and 3 for P2, as well as 4 milliseconds in the CPU. Therefore, its processing time is 31 milliseconds. That means that these 3 averaged 27.3 milliseconds of processing time. If we reorder these processes, placing P2 at the front and P1 at the rear of the queue, the whole picture changes. P2 takes only 3 milliseconds. P3 waits these 3 milliseconds as well as taking 4 milliseconds of its own. But P1 waits for 7 milliseconds and then takes 24 milliseconds for a total of 31 milliseconds. The average processing time drops to 13.7 milliseconds. This third scenario shows a mid-range value, which is representative of the other 3 cases. The next algorithm is usually called shortest job first, but it could be called shortest next CPU burst time first, because this is what we really want. The most important thing is to be able to come up with a reasonable approximation of what the next CPU burst can be assumed to be. In general, this will be the best scheduling algorithm if our approximations are reasonably accurate. We can show that if the predictions are accurate, this will be the algorithm with the absolutely shortest processing times. However, there are three problems with this. The first is that our predictions may not be so accurate. The second is that the operating system may eat up a lot of processing time doing the necessary calculations for these predictions. Lastly, a longer job may find itself waiting forever behind a steady stream of faster jobs. An analogy might be if we had a shopping cart of groceries and let people go in front of us if they only had one or two items. If there are enough people like this, we might wait until closing time before we could check out. This algorithm can work well as a preemptive or non-preemptive algorithm. In the former case, it becomes shortest remaining time first scheduling. Our best case from before is exactly what we get for shortest job first. And this is exactly what we should expect. The biggest problem is coming up with an accurate prediction of how long the next CPU burst will be for each process. The best way to do this is to take a look at the most recent history of the process's CPU burst time and extrapolate from there. An exponential average is most commonly used because it gives the greatest weight to the most recent bursts. The formula on this slide shows the power series that we can use to predict what our next CPU burst should be. In reality, we can use the previous burst in the calculations, so we can avoid having to calculate a power series from scratch just for a CPU scheduling algorithm.